Hello and welcome to the video for innovation experiment number 4, irrigation management. My name is Jakub Fuska and I am from Slovak University of Agriculture. For the beginning, I would like to introduce you to our team. Petr Piesecki for geoinformatics, Jakub Fuska for GIS, Jan Macura for cartography and GIS, Juraj Modransky for landscape planning, Efthymios Chrysanthopoulos for hydrology, and Anton Kantiza for digital agriculture technologies. Our experiment was focused on the help to farmers to estimate the amount of water that is currently stored in irrigation water reservoirs, such as small lake or dam. The information on the available water amount is crucial for the farmers so they can make the decision on irrigation planning, not just in accordance to crop requirements, but also to incorporate the available amount of water in water reservoir. Usually, the water reservoir have some kind of water level measurement, for example, water level gauge, but the amount of stored water at given water level is slowly decreasing as the result of reservoir siltation that occurs on every lake or dam as the result of erosion in watershed. Our goal is to create a simple tool that would continuously measure the water level and then calculate the water storage at given moment. To get the information, we are using the ultrasonic sensor that surveys the water level. We use this information within the calculation that is based on the water level elevation and digital elevation model of reservoir bottom. Reservoir bottom model is created from the sonar and GNSS survey to obtain the most current data of the bottom shape for most accurate volume calculations. As the study area, we chose the water reservoir in the village called Mania, located in Nové Zámky district in Slovakia. This reservoir was built with the purpose of irrigation, but currently the irrigation is not in operation. For this water reservoir, the digital elevation model of reservoir bottom and also the digital elevation model of watershed is available. Elevation of the water level can be surveyed in various ways. We decided to use the prototype of ultrasonic sensor that was developed by my student in his diploma thesis in 2018. This sensor is built on an Arduino platform and it sends the measurement data, the distance from the sensor to water level, via the GPRS modem to the database, which recalculates this value to water level elevation. Then the server calculates the current water storage. Calculated data should be loaded in the web page where the farmer can see what is the current water storage so he can make the decision on irrigation timing, dosage amount, and so on. This is the basic part that tells the farmer the current status, but with the use of available data and its processing, we would like to go further. We wanted to try to estimate the amount of water that will be recharged to reservoir during the forthcoming days if the rain event will occur. That means we would need to know the parameters of the water reservoir watershed, such as morphology, soil type, temperature, humidity, land cover, and land use, and also very important information on weather forecast. With the use of hydrological modeling, we would be able to know not just the current water storage, but also the water storage in the forthcoming days. With this information, the farmer can make better decisions as he can consider current amount of water, but also the near future, talking about few days in accordance to weather forecast. This experiment is built on foundations that were formed in 2017 when me and my student Richard, were dealing with his diploma thesis. The task was to create a simple map of current water depth of reservoir that can display the depth of water in any point of water reservoir, which would help the hobby fishermen to know the depth at a given location. We had literally zero experience with WebGIS solutions, so we asked Richard's brother Lukáš, who had an experience in programming, to help us. We created the series of map of water depth in a 5 cm step of water level elevation increment. Upon the water level sensor reading, the closest water level elevation was displayed. It was functional, but kinda messy approach. With this solution, we were able to create very simple web page hooked to GeoServer to display the current water depth. During the first Agrihub Hackathon in fall of 2021, we tried the different approach to calculate the map of water depth and water volume and water surface, let's say, on the fly, with the use of Jupyter Notebook. This project provided us with workspace, so thank you guys for your support. But this solution did not work very well for us, as the tools we were familiar with were not very usable for our case. We decided to go a different way, to build the solution on virtual server, and this solution was consulted with new member of the team, Petr Piasecki, who proposed to run the PostGIS server hooked to GeoServer and creating GrassGrid scripts for the spatial calculations. First task was to calculate the water level elevation with the use of ultrasonic sensor. As this sensor was previously tested to fetch the readings, we decided not to mount it in a real water reservoir, but just to simulate its readings with simple script that generates only the random values in the range of possible water level fluctuations. Then the water level elevation is calculated in PostGIS as the subtraction of sensor reading from sensor elevation. The sensor readings are stored with the date and time in PostGIS database. With the known elevation of water level, we are calculating the map of water depth with r.lake module of GrassGrid, which uses the digital elevation model of reservoir bottom and water level. The result is raster map of depth. This map is afterward converted to the polygon of water surface at given water level. This polygon contains also attributes of water volume and water surface, water level elevation, and date and time. We call this particular polygon the latest water surface, and it is accessible as WFS, WMS, and as a PostGIS entry. Then we append this particular polygon to the database of all previously calculated polygons. This creates the database and history of results. We are storing only the results of calculations, not the particular water depth maps as rasters. The next step was to incorporate the weather forecast for forthcoming days with considering the land use in the watershed to find out what amount of water will flow to the reservoir after the rain event. Our goal was to create the simple black box model that calculates the amount of water recharge as the percent of precipitation volume known from the forecast. Weather forecast was fetched from the Open Weather Map, which offers the API to get the current forecast for a particular region for next 7 days. The land use was derived from orthophotomap and the data was stored in PostGIS database. The calculation of water recharge is calculated for forthcoming days and stored in PostGIS. Only for current day, so no history can be accessed, for now. Later we would like to store also the history of forecast, so more advanced estimations based on forecast and real precipitation can be analyzed. We also wanted to try to incorporate the soil moisture and watershed terrain morphology in the calculation of water recharge. First, we needed to test the ability of our system to fetch the soil moisture sensor readings. For the purposes of the project, we teamed with company Plant Control IO, who helped us with the test with their existing sensor in operation. The sensor was not mounted in our study area, but it was enough to test the data communication between sensor and our system. It all worked well, and we were able to store the readings that were sent from sensor. We did not have enough time to place the real sensor in our study area, and we were also not able to make the modeling of soil moisture and terrain morphology effects of water recharge. In the future, this is the first thing we need to solve. This was caused by a lack of experts in the field of hydrological modeling. With the results of hacking, we were able to create the simple web page that displays the OpenStreetMap base map with polygon of the current water surface and dashboard with the numeric data, water level, water volume, and area of water surface. The forecast of water recharge for forthcoming 7 days is displayed as a simple table with dates and presumed volumes of water recharge. In the future, we would like to add the widget that will allow us to browse the history entries. This hackathon led us finally to first results. Some were failures, some were successful, but now we are able at least to see the current data and very basic forecast of water volume development. This is first step in our endeavor to be able to deliver the product, irrigation management decision tool for farmers. Our next step should cover the improvement of hydrology modeling, to incorporate the current soil humidity, the terrain morphology, and to improve the whole model of surface runoff. We met a lot of interesting people, for example, the guys from Plant Control IO and SenseLog. This could be the future partnership for us. Thanks to the activities in working packages 6 and 7 of this project, we are also in the process of considering the possibilities of the business development. This experiment was started only as the idea, but now we are thinking in more than just academic scope. And it also showed us that we are only at the very beginning. We have seen a lot of projects during the activities of Agrihub Czech and Slovak. We see that our project is making only its first baby steps, but the projects we have seen are really valuable inspiration for us. As we met a lot of people, we started some simple but promising cooperation. So let me say the great thank you, Smart Agrihubs and Agrihub Czech and Slovak, for this opportunity, experience, and all the support and help and all the knowledge you shared with us. You are the great, and I'm glad that we were a member of this project.